Hello everyone. So in the last videos you saw how to create and sample points into your project. So let's see how you can filter some of the points so you can control which points are you using for spawning stuff in your level and make your worlds more dynamic and feel a little bit more interesting. So let's start with looking an example here. I've prepared here a PCG graph that will make an example, for example, filling in toys into a kid's playroom. So I have downloaded a couple of toy models from Quixel and I'm just scattering them around with the surface sampler. So let's look at the PCG graph right now. So here is the graph. We have get the landscape data. We are using a surface sampler. Then we are transforming the points just to move them a little bit around randomly and rotate them. And let's delete this self-pruning and connect this to the static mesh spawner, which has 16 different toys connected to be placed randomly. So let's look now the result in the level. So you can see it's clearly randomly placing and rotating objects into your level. But let's see how the filtering can help us and the different methods you can use to apply filtering in your project. Open the PCG graph, and here I have chosen all of the nodes inside the filter category. So if you right click into your PCG graph, you have this filter category, and I have created all of the nodes, as you can see here, into this PCG graph. So we can look at each and every one of them. And I have taken some of the other categories which are still useful for filtering, like for example these Boolean nodes for difference, intersection, and union. And I have taken out here the merge points to show you what's the difference between the union and the merge points, and different special nodes like the select points here and the discard points or irregular surface. So we'll look into all of these nodes, and keep in mind that some of the nodes into the filter graph, like for example here the attribute filter and the filter attribute elements, as you can probably tell, they're exactly the same node. It has the same settings, it has the same name, so it's just a different way of calling it here into the presets that they give you into the different categories. So let's look again at this graph, and let's disconnect this mesh spawner just to start with the basic graph of just getting the landscape and sampling the landscape. So the surface sampler, let's connect a default one so I can show you what are the differences that I made to it. Let's connect a default surface sampler instead of this one into a debug node. So let me go a little bit back. So the default surface sampler has a point extents of 15 to each direction, and this means that each of these points will be 100 units big, because 50 is just in the one direction, so the extents goes to left and right, front and back, and up and down. So this 50 means the actual size will be 100 units, and you can clearly see that overlaid on the level grid, where every square is a single meter. This point is a meter long. This point extends by default is creating a 1 meter point. The points per square meter is 0.1, and if we go to 1, this means that for each square meter we'll have 1 meter big point. So the thing I changed here into the surface sampler is make the points a lot smaller in order to have a much bigger density, because if I inspect this node by right clicking and inspecting, you can see here that I have 36 of these points, because the size of my room is 6 by 6 meters roughly. So this is why it creates 6 points into each direction, and it cannot create more even if I put here 30 like I have here into my other surface sampler, just because the points are very big. If I start reducing the size of these points, like for example 555, I now can have much more points into each square meter than one, what I have before. So now it's able to create more points, and it's actually creating 1,000 or even more than 1,000 points. But we can work with that with filtering later. The exact values that I have here for the extents, I'll show you now how I decided on these values. These values are important if you want to make some filtering or other manipulations that are based on the bounding box of the object. For example, if you want to use this difference node or the self-pruning or something like this, which is taking the bounding box of the points that you're creating and intersecting it with other bounding boxes of the other points. And if you're not doing any spatial managing of the data, it doesn't really matter. You can have lower values which work just to achieve the density you want. But if you want to actually intersect the objects and control how they place based on the real size of this bounding box, you need to pay attention what values you put here. And I'll show you now how I decided on these values. So these are all the models that I downloaded here from Quixel. For example, this is the cube, this is some roof, and I have some animals. So I shift select all of the toys that I will be placing in the level and place them into a single place in the level. And in that way, when they are overlaid on top of each other, I can now make a very good assumption of what this bounding box should be size-wise. So let's create a cube shape, and let's copy the position of this point by selecting some of these toys here, copying the location into the details panel. And then if I search here for cube, this cube 2 is the one that I just created. I'll paste the location and let me zoom out. The cube by default is 1 meter by 1 meter or 100 units in Unreal Engine. So I'll scale it to 0.5. It's still too big. Then 0.05 on each direction. And you can see now it's a little too small. And I'll start increasing this size. For example, into the X direction, which is this green arrow, I'll put 0.1. And it starts to look a little bit closer, but I still need it to be a little bigger. So 0.12. And now I feel like into the X direction, it's roughly the size that I need to use in order to estimate the size of each of these toys a little bit closer. So into the green arrow, I still need a little bit of bigger bounding box. So 0.1 is a little bit too big. So let's do a 0.08 or 0.07. So now I believe it's a very good representation of the shape. And here into the Z direction, which is the vertical one, 0.3 is the right size, I believe, to properly estimate the size of these toys. And it doesn't really matter that some of the toys stick a little bit outside because it's high up from the ground and it will not interfere with the other toys if they're placed close to each other. So these values, 0.12, 0.07 and 0.3, are the sizes of this bounding box in order to fit the toys inside. And if you look closely at the surface sampler that I have here, this 6, 3.5 and 15, these are derived exactly from this. It's half the value of this because the extends both directions. So 6 times 2 is 12, and this is 0.12 because it starts with from 1 meter default size. So we need to divide it like 100 times in order to get the actual Unreal Engine unit size. And here we are entering the actual unit size for Unreal. So this is why I have 6 here, half of this 12 centimeters, then 3.5, half of this 0.07, and 15, which is half of this 30 centimeters here. Doing it this way, it will create, let me delete all of these toys from here, and we'll have all the points into our graph created. So let me delete this one and connect this surface sampler that I have. So each of these points represents very good the size of the toys that I want to place. And you can see we connected it to the debug node in order to see the actual representation in the level. If I delete this debug, I can enable the debug on the surface sampler itself, and it will show me the same thing, the bounding box of each of the generated points, which is set up to represent the shape of the toy I want. And then we are creating these transform points just to randomize the position a bit, so they're a little bit too arranged right now. So if I connect these transform points and now I debug only selected, so Control Alt D, these transform points, you can see it's moving 100 units in one or the other direction, in the x-axis, in the y-axis, and this random value between -100 and 100. We'll look at these transform points maybe into the next tutorial a little bit with more details. The next tutorials will be about modifying the points and the data into the points, but I'm using it here just as an example to randomize a little bit the position and also the rotation. And just for easier visualization right now, let's remove the rotation randomization. Let's go to 0 here. So all will be facing the same way right now, but the position will be a little bit randomized with this offset min and max values for x and y. And I'll connect it to the static mesh spawner, where I created here 16 values. And the easiest way to create multiple values with different meshes, if you click here this add element 16 times, because you know you have 16 toys, and then search for static mesh, you can see it will list only the static mesh value for each of these 16 inputs, and then you can very easily drag from your level here each of these different toys. For example, here where I have this caterpillar, let's redo it like this. So if I clear this, this is how it comes by default, and you can just drag into the static mesh field the toy mesh that you want and do it for the 16 values of all the mesh entries, and you have the same static mesh spawner as me. So again, we'll look at this into a future tutorial with all of the settings, but for now we are just placing all the static meshes inside, and it will be enough just for the demo. So if I connect these transform points to the static mesh spawner, and if I remove the debug, and let me go back to the level, you can see we are now spawning all toys inside this room that we created. And you can clearly see a couple of problems. So first of all, we are spawning points outside of the room. So the room is defined by this cube, which is our PCG volume, and this is the size that I want to place the toys inside. And because we are using a random transform for all the points, they are sometimes going outside this room. And the other problem that we can see is some of the toys are overlapping each other. So at some places you can see we have a lot of toys just going into each other, which is not possible into the real world. So we need to fix this. So we can use filtering of the points to achieve solutions for these problems. So let's look at the first problem, how we can get rid of these toys outside of this box. So if we go back to our PCG graph, we can use the Cull points outside actor bounds node. And if I connect it here, let's disconnect this. You can see it's deleting all of the points that are outside of this graph. let me connect back the transform points directly to the static mesh spawner, and then you can see we have the points outside, and if I disconnect it and I only have the connection going through the Cull points outside actor bounds, it will delete all of the points from the outside. So this gets rid of one of our problems. And this is one way of filtering the points, because if I inspect these transform points, you can see we have 1075 points before culling the outside points. And if I inspect the next node, we now have 907 points. So we get rid of 100 and something points, 170 points roughly, that were outside, and we are now spawning meshes only for the points inside. So the other problem can be solved by doing self-pruning, which if you search for self and go here into the filter category, you will find this self-pruning node. So let's disconnect the static mesh spawner and connect it to the self-pruning node. And now if I inspect these Cull points, we have 907 points. If I inspect the self-pruning, we have 638. So we get rid of around close to 300 points that were intersecting the other points. So let's zoom in somewhere. And you can see we no longer have points that are toys that are intersecting each other. All of the points are just unique toys scattered around. And let me show you what I meant earlier, that it's important to set bounds properly. So if we go back here to the surface sampler, if we disconnect this self-pruning, let's connect this to the static mesh spawner directly. So we are now spawning static meshes on all of the points we had. Let's change the value of some of the extents and show you that it can create some problems. In order to better illustrate, I'll create an extents modifier here, and I'll connect it between them. So let me disable the static mesh spawner and just work with the debug. So I'll change this extents modifier to multiply mode, and by multiplying by 0.1, for example, I can change this extents value to a smaller value, and you can see that these boxes are no longer overlapping. And this means that this self-pruning node will not remove them. So if I enable the static mesh spawner, you can see I have clearly toys that are intersecting each other. But because of my bounds are not properly set up, this extents modifier is making them smaller into one of the directions. And in order to see better the toys inside, let's go into this debug node and change this cube visualization with this wireframe cube. So now we have this, just the outlines of these cubes, a little bit easier to see what's inside. So if I start to increase this extents multiplier, 0.2, 0.3, 0.4, 0.5, you can see they're closer and closer to each other. And when I go to 0.6, they are now overlapping. And this is why one of them becomes deleted. So if I go back to 0.5, I can see this cube, but if I put 0.6, now the bounds have enough area to overlap each other, and this self-pruning is removing one of them just to keep one not intersecting with each other. By properly setting up the bounds into our surface sampler, like we did to the 6, 3.5, and 15, that we know will match our toys exactly, we can be sure that when we use the proper bounds, the self-pruning will delete all the toys that are intersecting with each other. And into the self-pruning node, you have a couple of different options. So large to small, small to large, all equal, none, and remove duplicates. So what this pruning type means is how it will decide which point will remove. So for example, if I go here again and do a debug node, and let's do some random scale for our points. So for example, from 1 to 3, and let's find some area right here, for example. Let's reduce a little bit the points per square meter so it's easier to see. So 20, and let's find some area with different size boxes. Here, this gray box and this black box. The gray box, the lighter one, is bigger than the black box. So if I go here to the self-pruning node, and if I choose the large to small, if I connect this debug after the self-pruning, you'll see that it will keep the lighter box. So it will prioritize keeping the large box instead of the small box. If I change this pruning type to small to large, it will keep the smaller point, not the larger one. So you are telling it here how to prune the points. So if I put none, it will not delete any of the points, so I'll still have this overlap. If I put large to small or small to large, it will prioritize the ones that are smaller or larger. Remove duplicates will remove only points that are matching all the data into the position and size, everything it's the same, so it will only remove duplicates. That's why it's not removing these points, they're different from each other. So the most used values here will be large to small and small to large. So let's keep it to large to small like it was by default. Let's go back and remove the scaling randomization. So we'll go back to 1, and let's increase again our points per square meter to 30. So now that you understand how the boxes are intersecting with each other, I'll put again the random rotation here to have just more interesting scene into our viewport. So I'll put 360 into the Z direction, and you can see that this self-pruning will take into account the rotation as well. So after we rotate the points, it will make sure that the bounds of all points are not intersecting each other. So this is the very, very useful purpose of this self-pruning node, to make sure that all of your points in the set are not intersecting each other, again, based on their bounding box, because before we spawn these static meshes, we only have this bounding box. It doesn't know what's the static mesh, how it will look like, so you need to make sure that you set up the bounding box correctly. So after you make sure by the self-pruning node that you don't have anything intersecting with each other, and with these cull points outside bounds, that you don't have anything going outside the area that you want to spawn in. The next thing will be intersecting some different bounds. So let's create another surface sampler. Let's connect it to the landscape data, and this time let's create some bigger points, for example 50, 50, 50, and let's connect this to a debug. So we are creating bigger points into our level right here, but let's create a lot less of them. So 0.1, something like this. So we have few points into our level, but with a bigger area. And let's increase the area even a bit more, 75, 75, 75, something like this. Let's create another transform points, and these transform points will add a little bit of random scale, a little bit of random rotation, and the same random movement that we have for the other points, 100 into and minus 100 into X and Y directions, min and max, something like this. So let's say we want to have toys only in these areas, or everywhere except these areas. So this is where you use this spatial filtering things by nodes that are based on the bounding boxes of the points that you create. So objects that are coming here from this self-pruning, let's connect them to a difference node. And this different node, we'll set it to binary. This means that it will either keep it or remove it. So this is the most used option into the difference node. And we'll connect this to the debug node. So these are the original points coming from the self-pruning. And if I connect this transform point to the difference of this node, let's connect it right now. And you can see we are removing the areas that we had these other bounding boxes of the other surface sampler that we connected. So this is what the difference does. It takes the original points and removes all the points that are intersecting with the other bounding boxes that you connect here into the difference. And if you want the opposite to be true, so you only want the points that are intersecting, then you can use this intersection node. So let's connect this intersection. Let's connect the original points to the source of this intersection node. Let's connect the bigger points that we generated with the other sampler into the source one. And now let's connect this to the debug. And you can see we now have the exact opposite result. So we have only the points that are intersecting with these cubes. And if you don't want to have this intersection like clearly with straight points after it, you can do a transform points, add some random positioning to the X and Y values, connect this to the debug. And now you can no longer see it's just intersecting cubes. And we'll again need these Cull points outside actor bounds, because here where we have the area into the edge of our room, if we randomly move some of the points that you can see now, if I mark the debug onto these transform points, it's moving some of the points outside the room, but we are using these Cull points outside actor bounds in order to get rid of these points. And we don't need this one anymore, because we can only do it here at the end, and it will get rid of all of the points that are outside the actor bounds. So now if we spawn with our static mesh spawner, we'll only have the toys that are intersecting with this other cube. So you now have much more realistic representation of toys inside the room. So because they will not be uniformly placed everywhere, they will be into some areas of the room, and you can control the randomization of this with these two surface samplers, the density, the size of the points, and everything like this. So let's continue with some other examples of how you can filter the data. For example, if you want to get only the points that have this giraffe toy, and you want to make some spawning on top of these points additionally. So for example, if I inspect this static mesh spawner, you can see here at the end, it will add another value which will contain the static mesh that you have connected. For now, just make sure that the node that you're connecting after will refer to this, because this is the last modified value. So if I mark this and inspect this, you can see that the last attribute is this none value. So everything is fine. It will work with this last attribute. So we can find the giraffe toy, the actual value for this giraffe toy, by connecting here to visualize attribute node. So this visualize attribute node will show you the value for this giraffe. If you find the giraffe here into your level, it will show you the index of the point, which in this case is 32. So if we go back here into the beginning of our data, if we scroll down to the 32nd point, if we double click on it, you can see that it will mark this point and it will properly be a giraffe value. So we can copy the value for this, copy to clipboard. And if I paste this into Notepad, you can see these are all the values for our point. And here the last value is the value that we have for our giraffe static mesh. So if I copy this value, then we don't no longer need this visualized attribute. We will do filter and we'll do an attribute filter. So this attribute filter, let's check. Here we have the conditions, the operator that we want to use. So let's use the equal operator. Let's mark the use constant threshold. So this will compare an attribute from your data. And right now we'll use the last modified attribute, which for this node is this column at the end, referring to the static mesh. So we'll compare the last attribute, the static mesh attribute, with a string value of our mesh. So make sure use constant threshold is checked. That way you have here the type and the value for your attribute. The type will be string. And why that's string? Because here at this static mesh spawner, you can see into the parentheses that the type of this attribute is string. This is why we need to choose string here, and the value will be the one that we copied. And right now, if I connect this to a debug node, and if I go back here a little bit, you can see that this debug is showing all the points that are containing this giraffe. So if I enable and disable this debug, this filter is returning all the points containing this giraffe inside the filter. And outside the filter are all the other points. So all the other points that are spawning into the level are now outside this filter. And the nice thing about the static mesh spawners is that they will apply the actual size of the object that they spawn to the bounds. So you can see that all the bounds are changed to the very, very closely matching box outside each different toy. So this is very useful for future modification into your graph. So let's right now work with the points that are inside this filter. So all the giraffes, and I'll show you other type of filters right now. So this is the first filter into our filter graph. The second one is this filter by range. So the filter by range works very similarly to this one, the filter just by attribute. So filter attribute filter range. Let's say that we'll filter in again the last value, which again will be the, or not the last value, let's filter something else. For example, let's filter the $sign index, which is the index of our giraffe. Let's mark the use constant for min and max, and the type for the index is an integer. So let's change the type to integer, and let's, for example, from 0 to 5, let's filter those. So if I connect this inside filter to the debug, you can see now I'll have some of the giraffes marked into this debug. So I'll have 1, 2, 3, 4, 5 giraffes, and here 6th one, because the indexes start from 0. So 0, 1, 2, 3, 4, 5. These are 6 indexes total, but all the indexes over 5 will be not inside this filter results. They will be outside this filter. So if I connect the outside filter, these are the other giraffes. So with this filter by range, you can filter by minimum and maximum value. This filter by attribute, it's just filter by single value. For example, all that are equal or less than or greater than or not equal, something like this. But this filter by range, it will always filter between these two ranges. And right now, because I have 0 as the first one, it's the same as filtering just by less than the max, but you can control this range by changing this. For example, if I put 2 here, and if I inspect the data here, before this filtering, if I go to the, let's connect this to the debug so we can see the ones that are filtering. So if I go here before the filter, and if I go to the 0 value, then 1 value, you can see we are not showing a debug over them. But if I go to the 2, we are now having this debug. Then 3, having again, 4, having again, 5, 6. So the 6 doesn't have it. So this filter by element, which we have connected to the debug, because we have the min from 2 to 5, this means that only the elements here from 2 to 5, so these 4 elements, will be inside the filter results. So let's say that for these 4 points that we have right now, we want to do a static mesh spawner, and we want to spawn, for example, this teddy bear toy on top of the other toys. So let's go back to our Megascans 3D folder, filter the static meshes, and find this teddy bear and connect it here into our static mesh. So if I click here onto the second point, let's disconnect the debug, and you can see that we now have this teddy bear on top of the giraffe. So let's do a transform points, so we don't have this problematic placement with the intersection. We'll rotate this teddy bear 90 degrees and we'll move it 2 units to the back and 5 units up, so like this. So you have now 4 giraffes with a teddy bear over them, filtered in this filter by range, and then static mesh spawner with this teddy bear on top of them. And all the other giraffes which are outside this filter doesn't have this teddy bear on top of them. For example, these giraffes right here don't have this teddy bear, but this giraffe here has it. So you can see how filtering is allowing you to show different results for different points, just filtering the data in the way you need it. So let's go back here to all the nodes that I showed you here. So these are the ones that I already showed you. Let's continue to the others. So the density filter. The density is the value that, let's go back here at the beginning and connect this to the debug. So the density is the value that you have here into the color representation. So the black values are density closer to 0 and the lighter values are density close to 1. So if I connect the density filter, so here when we are connecting all of our generated toys to this intersection, let's first put a density filter and let's connect this to the debug, the density filter to the debug. So, but the density filter has lower and upper bound. So if our lower bound is 0 and the upper is 1, it doesn't filter anything. So this self-pruning, let's inspect it. We have 649 points. The density filter has the same 649 points after it, because all the values of the densities are between 0 and 1. We are not filtering anything. But if I put 0.5 as the lower bound, you can see into our level, we are only left with the lighter points. So where the density is over 0.5. And right now we have 341 points instead of the 649 that we start with. So we are just taking the points having higher density than 0.5. Or we can do it the other way. The lower bound can be 0, the upper bound can be 0.5 or 0.3. So we are taking just some of the points that have this density in this range that we set up here. And you can change this range based on the amount that you want and the colors that you want here. The ones that are closer to the white value are higher density, and the ones that are darker are lower density. So by filtering the density right here, you are getting again some randomization. There again we are intersecting and so on and so on. So we are doing the same but just on a smaller set of values in order to get some randomization into our level. So let's continue with other filters. So the next filter is filtering data by attribute, by index, or by tag. So filtering data by any of these values. This means that you have different data sets. So if you don't know what are data sets, go back to the first tutorial of this series, which explains the data sets. But let's say that I connect here a transform points node, which will not do anything. We'll just use it to combine two data sets inside one node, and then we'll connect it to a attribute filter or filter data by attribute. So let's say that this density filter, or actually we'll need another attribute to be present. So let's connect the points here after the static mesh spawner, and let's output the name of our mesh inside this attribute spawner. Instead of the value named none, let's name it mesh, like this. So this filter data by attribute, let's filter by existence, and the attribute will be mesh. So here, these transform points, if I inspect this node by right-clicking and inspect or clicking A, this contains 649 entries into the first data set and 86 entries into the second data set. But if I go here into the filter data by attribute, it only contains these 86 entries by the second set, because all of the values in the first set here does not have this mesh attribute, which is added here only to the second set that we connected. So this filter data by attribute will return you inside the filter only here the nodes that contain this mesh attribute, and outside the filter it will return you all the other points. So this is why filter data by attribute means that it will filter the data that has, and the other two that I showed you are by the index and by the tag. So if I again have these two data connected here, and one of them has index 0 and the other has index 1, so filter data by index, and the select index will be 0. Let's connect this to the debug. So we are filtering only the data coming here from the data set with index 0, so 649. If I inspect this, 649. And if I change the index here to 1, we are only filtering the data from index coming from data set with the index 1. And that's why we have 86 values. So filtering data by index is filtering by the dataset index right here. So we are having two datasets coming in here into the input, these two datasets, and we are filtering by the index of these datasets. The same is with the tag. So the tag of the dataset will be checked. So let's continue by the next nodes we have into the filtering, because this is the same, but instead of index it's using the tag. So the next node, this removes empty data. Of course, it will remove data that does not contain anything. So dataset that is empty, it will remove it. So it's not really interesting in our current example. We'll use it in the future probably, but I'll give you example then. So this self-pruning we already saw. This data filter by type, it's usually automatically created between some nodes that just use a particular type of data. So you can choose, for example, point or spline or curve or different type of data. And you can see that the second pin is changed. So it's filtering only the data that's this type. So it's filtering only points or only attribute sets. So this is important when you are creating graphs that require a specific type of data and you want only the data coming to be a single type, but it's just more advanced feature. Or so let's continue to the next node, filter elements by index and this random choice. So for example, here, instead of filtering elements by range, which we did with range of indexes between 2 and 6, let's do a random choice. So this random choice, let's stop debugging this. Let's remove all of this. So here, this random choice will select just a single giraffe from the data we had here. So we had 7 giraffes, and this random choice will just choose one of them and it will continue the graph with just the chosen one. If we put 2, it will choose 2, so this one and this one, and it will continue the graph next to spawn this teddy bear on top of it, just for the 2 that it chooses. And this is the fixed mode. If you uncheck the fixed mode, you'll have a ratio. So 0.5 will pick 50% of the points, and 0.1, 10% of the points. 1 will pick all the points, so it's not a choice, it's just picking everything. But if you say, for example, put 0.5, it will pick 50% of the point to continue with this chosen pin, and all the other else will be onto this discarded pin. So for example, if I connect, let's find a giraffe that doesn't have it. For example, here, this giraffe at the back has the teddy bear and this doesn't. So if I connect the discarded to continue the same graph as the chosen ones, it will put teddy bears on the discarded as well. And I can uncheck the chosen ones. So you can see the chosen ones don't have the bear, only the discarded points have the bear. So this is choosing 50% into the chosen and 50 into the discarded, and you can control the ratio here or the number if it's the fixed mode. So this is what the random choice does. And let's check this thing, filter elements by index. It's similar to the filter that we created before, because we choose for the attribute to filter by index attribute, and of course this can do the same, filter the elements by index, and the index, let's say, will have index of 0. Let's change it to an integer type. So if we show by visualizing the attributes of the points, so you can see that the giraffe here is with index 6. So if we connect 6 to our filter elements by index, you can see that the giraffe with index 6, which we saw by visualizing our attributes and seeing here into the brackets that it's the 6th giraffe, here it's the one with index 5. So if we change to index 5, you can see it will disappear here from the index 6 and it will appear here on the index 5. So let's change now the data to 5. Sorry, this is 3, not 5. So yeah, it disappeared from 6 and it went here onto index 3. So filter elements by index, it will return you the ones with the indexes that you connected. So if you connect multiple indexes, so let's say 5 and 3, or it was 6, the other one was 6. So let's connect 6. So it will put the one on the 6 and one on the 3. So, but all other giraffes will not be selected. Where we have giraffe, like here, we don't have anything because we only connected these indexes to be filtered. And this is everything for the filters inside the filter category. So let's see what these select points will do and these discard points on irregular surfaces. So if we go here after this random choice and do a select points, this select points is similar to this random choice. So you give it a ratio, for example, of 0.5, and it will take these 4 points and it will select about half of them. And the difference is that this select points doesn't really select mathematically half of them. It will select half of the values based on some randomization. So it will not be always 50%. It will be, if you do it multiple times, it will be close to 50%. But as you can see right now, from 4 values, it will just select a single one. And if I change the seed, it can be here, it's selecting 4, now it's selecting 2, now it's selecting 1. So it's most probably close to the 50%, but it's not always strictly 50%. But this random choice is always 50%. The ratio that you set is very strictly mathematically correct. So this select points also doesn't give you the discarded points, and that's why I prefer much more the random choice node. So I don't really use this select points a lot. So let's see the last filtering node that we didn't check still, and it's the discarded points on irregular surfaces. And for the surface, we'll connect our landscape data. Let's connect this for now to a debug node like this. And let's go into our landscape and I'll modify it a bit to have some very tall area right here. So let's go into our selection. So right now, if I disable this discard points, or let's do it like this. So if I connect all my original points to our debug node, you can see I have a lot of points on this irregular surface in the landscape. But if I connect these disregard points on irregular surface, it's removing the points that do not match the surface. So their extents value, and you can control it with this multiplier, how much of their extents value you want to take. So the multiplier of 1 means that the exact extents of your toys, and you can put it like 2, for example, 2 times bigger area around them. You want to be inside of a height threshold. So how much centimeters up and down, or Unreal Engine units up and down, you allow the area to be not even in order to place this point. So guys, I hope that these examples on filtering points inside Unreal Engine PCG graphs will help you to create more structured graphs and to closely achieve what you're looking for with the procedural content generation framework. And in the next tutorial, I'll show you how you can manipulate the data, add attributes, manipulate those attributes in order to filter based on those values and achieve better systems with that. And if you want to watch these tutorials earlier, join the channel into the higher ranks. If you like this tutorial, subscribe for the channel, like this video. And guys, I'll see you in the next one. Bye.